High dynamic range imaging is a set of techniques used in imaging and photography to reproduce a greater dynamic range of luminosity than possible using standard digital imaging or photographic techniques. HDR images can represent a greater range of luminance levels found in real-world scenes, from direct sunlight to faint nebula. It is often achieved by capturing and then combining different exposures of the same subject matter. Non-HDR cameras take photographs with a limited exposure range, resulting in the loss of detail in bright or dark areas. HDR compensates for this loss of detail by capturing multiple photographs at different exposure levels and combining them to produce a photograph representative of a broader tonal range. The two primary types of HDR images are computer renderings and images resulting from merging multiple low dynamic range or standard dynamic range photographs. HDR images can also be acquired using special image sensors, like oversampled binary image sensor. Tone mapping methods, which reduce overall contrast to facilitate display of HDR images on devices with lower dynamic range, can be applied to produce images with preserved or exaggerated local contrast for artistic effect. Photography. In photography, dynamic range is measured in EV differences between the brightest and darkest parts of the image that show detail. An increase of 1 EV, or 1 stop, represents a doubling of the amount of light. High dynamic range photographs are generally achieved by capturing multiple standard photographs, often using exposure bracketing, and then merging them into an HDR image. Digital photographs are often encoded in a camera's raw image format, because 8-bit JPEG encoding doesn't offer enough values to allow fine transitions. The images from any camera that allows manual exposure control can be used to create HDR images. This includes film cameras, though the images may need to be digitized so they can be processed with software HDR methods. Some cameras have an auto-exposure bracketing feature with a far greater dynamic range than others, from the 3 EV of the Canon EOS 40D, to the 18 EV of the Canon EOS 1D Mark II. As the popularity of this imaging method grows, several camera manufacturers are now offering built-in HDR features. For example, the Pentax K7 DSLR has an HDR mode that captures an HDR image and outputs a tone-mapped JPEG file. The Canon PowerShot G12, Canon PowerShot S95 and Canon PowerShot S100 offer similar features in a smaller format. Even some smartphones now include HDR modes, and most platforms have apps that provide HDR picture taking. Color film negatives and slides consist of multiple film layers that respond to light differently. As a consequence, transparent originals feature a very high dynamic range. Camera characteristics such as gamma curves, sensor resolution, noise, photometric calibration and spectral calibration affect resulting high dynamic range images. Tone mapping. Tone mapping reduces the dynamic range, or contrast ratio, of an entire image while retaining localized contrast. Software. Several software applications are available on the PC, Mac and Linux platforms for producing HDR files and tone-mapped images. Notable titles include: comparison with traditional digital images. Information stored in high dynamic range images typically corresponds to the physical values of luminance or radiance that can be observed in the real world. This is different from traditional digital images, which represent colors that should appear on a monitor or a paper print. Therefore, HDR image formats are often called scene-referred, in contrast to traditional digital images, which are device-referred or output-referred. Furthermore, traditional images are usually encoded for the human visual system, which is usually called gamma encoding or gamma correction. The values stored for HDR images are often gamma compressed or logarithmically encoded, or floating point linear values, since fixed point linear encodings are increasingly inefficient over higher dynamic ranges. HDR images often don't use fixed ranges per color channel other than for traditional images to represent many more colors over a much wider dynamic range. For that purpose, they don't use integer values to represent the single color channels but instead use a floating point representation. Common are 16-bit or 32-bit floating point numbers to represent HDR pixels, However, when the appropriate transfer function is used, HDR pixels for some applications can be represented with as few as 10^12 bits for luminance and 8 bits for chrominance without introducing any visible quantization artifacts. History of HDR photography, mid-19th century. The idea of using several exposures to fix a too-extreme range of luminance was pioneered as early as the 1850s by Gustave Le Gray to render seascapes showing both the sky and the sea. Such rendering was impossible at the time using standard methods, the luminosity range being too extreme. Le Gray used one negative for the sky, and another one with a longer exposure for the sea, and combined the two into one picture in positive. Mid-20th century, manual tone mapping was accomplished by dodging and burning selectively increasing or decreasing the exposure of regions of the photograph to yield better tonality reproduction. This is effective because the dynamic range of the negative is significantly higher than would be available on the finished positive paper print when that is exposed via the negative in a uniform manner. An excellent example is the photograph Schweitzer at the Lamp by W. Eugene Smith, from his 1954 photo essay A Man of Mercy on Dr. Albert Schweitzer and his humanitarian work in French Equatorial Africa. The image took 5 days to reproduce the tonal range of the scene, which ranges from a bright lamp to a dark shadow. Ansel Adams elevated dodging and burning to an art form. Many of his famous prints were manipulated in the darkroom with these two methods. Adams wrote a comprehensive book on producing prints called The Print, which features dodging and burning prominently, in the context of his zone system. With the advent of color photography, tone mapping in the darkroom was no longer possible, due to the specific timing needed during the developing process of color film. Photographers looked to film manufacturers to design new film stocks with improved response over the years, or shot in black and white to use tone mapping methods. Film capable of directly recording high dynamic range images was developed by Charles Wyckoff and EG&G in the course of a contract with the Department of the Air Force. This EXA film had 3 emulsion layers, an upper layer having an ASA speed rating of 400, a middle layer with an intermediate rating, and a lower layer with an ASA rating of 0.004. The film was processed in a manner similar to color films, and each layer produced a different color. The dynamic range of this extended range film has been estimated as 1/108. It has been used to photograph nuclear explosions, for astronomical photography, for spectrographic research, and for medical imaging. Wyckoff's detailed pictures of nuclear explosions appeared on the cover of Life magazine in the mid-1950s. Late 20th century, the concept of neighborhood tone mapping was applied to video cameras by a group from the Technion in Israel led by Professor Y.Y. Ze'evi, who filed for a patent on this concept in 1988. In 1993 the first commercial medical camera was introduced that performed real-time capturing of multiple images with different exposures, and producing an HDR video image, by the same group. Modern HDR imaging uses a completely different approach, based on making a high dynamic range luminance or light map using only global image operations, and then tone mapping this result. Global HDR was first introduced in 1993, resulting in a mathematical theory of differently exposed pictures of the same subject matter that was published in 1995 by Steve Mann and Rosalind Picard. The advent of consumer digital cameras produced a new demand for HDR imaging to improve the light response of digital camera sensors, which had a much smaller dynamic range than film. Steve Mann developed and patented the Global Hdr Method for producing digital images having extended dynamic range at the MIT Media Laboratory. Mann's method involved a two-step procedure: generate one floating point image array by global-only image operations, and then convert this image array, using local neighborhood processing, into an HDR image. The image array generated by the first step of Mann's process is called a light space image, light space picture, or radiance map. Another benefit of global HDR imaging is that it provides access to the intermediate light or radiance map, which has been used for computer vision and other image processing operations. In 2005, Adobe Systems introduced several new features in Photoshop CS2, including Merge to HDR, 32-bit floating point image support, and HDR tone mapping. video. While custom high dynamic range digital video solutions had been developed for industrial manufacturing during the 1980s, it was not until the early 2000s that several scholarly research efforts used consumer-grade sensors and cameras. A few companies such as Hdr have been developing digital sensors capable of a higher dynamic range. Red Epic X can capture HDRX images with a user-selectable 1 to 3 stops of additional highlight latitude in the X channel. The X channel can be merged with a normal channel in post-production software. With the advent of low-cost consumer digital cameras, many amateurs began posting tone-mapped HDR time-lapse videos on the Internet, essentially a sequence of still photographs in quick succession. In 2010, the independent studio Soviet Montage produced an example of HDR video from disparately exposed video streams using a beam splitter and consumer-grade HD video cameras. Similar methods have been described in the academic literature in 2001 and 2007. Modern movies have often been filmed with cameras featuring a higher dynamic range, and legacy movies can be upgraded even if manual intervention would be needed for some frames. Also, special effects, especially those in which real and synthetic footage are seamlessly mixed, require both HDR shooting and rendering. HDR video is also needed in all applications in which capturing temporal aspects of changes in the scene demands high accuracy. This is especially important in monitoring of some industrial processes such as welding, predictive driver assistance systems in automotive industry, surveillance systems, to name just a few possible applications. HDR video can be also considered to speed up the image acquisition in all applications, in which a large number of static HDR images are needed, as for example in image-based methods in computer graphics. Finally, with the spread of TV sets with enhanced dynamic range, broadcasting HDR video may become important, but may take a long time to occur due to standardization issues. For this particular application, enhancing current low dynamic range rendering video signal to HDR by intelligent TV sets seems to be a more viable near-term solution. Example: this is an example of 4 standard dynamic range images that are combined to produce 2 resulting tone-mapped images. Original images. HDR sensors. More and more CMOS image sensors now have high dynamic range capability within the pixels themselves. Such pixels are intrinsically non-linear so that the wide dynamic range of the scene is non-linearly compressed into a smaller dynamic range electronic representation inside the pixel. Such sensors are used in extreme dynamic range applications like welding or automotive. Some other sensors designed for use in security applications can automatically provide 2 or more images for each frame, with changing exposure. For example, a sensor for 30 fps video will give out 60 fps with the odd frames at a short exposure time and the even frames at a longer exposure time. Some of the sensor may even combine the 2 images on chip so that a wider dynamic range without in-pixel compression is directly available to the user for display or processing. See also. References